Hello everyone, welcome to another video of From Concept to Circuit. In this video, we want to make a very interesting project to look at the electromagnetic waves around us. We are going to use the spectrum analyzer we made with ADALM Pluto in the previous video and use that to look at the RF signals and electromagnetic waves around us. What we want to do is use that spectrum analyzer, connect a wideband antenna at the receiver port of our ADALM Pluto, then set a frequency sweep, for instance, 100 megahertz to 6 gigahertz, and see what is the spectrum that is captured by the antenna. Then we can use this to identify any known bands around us, for instance, Wi-Fi, Bluetooth, GSM, LTE, or AWS. And also we can use this to detect any anomalies around us. For instance, we can what we have done in this video is we create a dictionary that we put any known bands inside it, for instance, Wi-Fi or Bluetooth, and based on that dictionary, we create some masks that show in the plot uh, the known bands that we are aware of, and then we can use those masks to see if any tones that is outside of those masks uh, needs more investigations because it's not the frequency that we recognize. For instance, in the dictionary that I have made, I have determined the Wi-Fi. As you know, Wi-Fi usually nowadays in the new generation of Wi-Fi that is inside homes, we operate at ISM band either 2.4 gigahertz or Wi-Fi 5 gigahertz, or for instance Bluetooth GSM, which is the previous generation of cell phones, or LTE and AWS for uh, more newer generation of cell phones. By the way, I'm uploading the code that I talk about in this video in the GitHub. Please feel free to go and look at the code, download it, and use it, and give me any comment about the code. And also, if you are interested in knowing more about these topics, please share this video, like, and uh, write more comments for me and subscribe. I'm going to talk about all RF interesting ideas, for instance, more advanced modulation techniques uh, in the future videos. Okay, so just as a recap for the previous videos, I want to talk about how we made this spectrum analyzer. What we did was we used a very powerful technique, which is called lock-in amplifier, to identify in a very noisy environment that might several frequencies exist. What we did was we multiplied our received signal to a sine tone with the frequency that we are interested in, and also a cosine tone. After some mathematical simplification, it turns out if we uh, simplify the equation and also do some filtering to remove any time varying information, we end up with two terms, am over 2 cosine of phi and am over 2 sine of phi, which can give us the amplitude information and phase information of that sine tone in our spectrum. This is a very powerful technique because we can use this in a very no in if a very noisy signal is received at a receiver, to just look at the frequency that we are interested in and identify its amplitude and phase. Um, and because of this filtering, we can also greatly reduce any random noise that we have um, in our signal. Another thing is, as I mentioned, assume that not only we can greatly reduce the random noise, we can also eliminate the effect of all other frequencies at the spectrum that we are looking at. Because, for instance, let's say we are interested in F2. and our received spectrum contains F1, F2, and F3. Because we are multiplying our just sine of 2 pi F2 to this equation, after some simplification, it turns out the only time invariant term in the equation is the one that contains the information of AM2, like the F2 frequency, amplitude, and phase. The rest have a time varying information in it. So even let's say F1 is very close to F2 because we can apply a very good low pass, a very low frequency, low pass filter. We can eliminate these terms from the final equation, and we end up only with AM2 cosine of phi 2, right? It means that no matter uh, of how F1 is close to F2 or F3 is close to F2, if F2 is very well defined, if we can first generate F2 with very good accuracy, with very low phase noise, we can surely after low pass filtering, we can eliminate any effect from F1 and F3. This is very useful because even if F1 is, let's say, 100 kilohertz only apart from F2, if our F2 accuracy of F2 is within like 1 kilohertz or lower than that, we can effectively only look at F2 and remove all other tones after this technique. This is why our spectrum analyzer it's behaving very good because it eliminates the noise and also eliminates the information of other frequencies. This is why this technique is called locking amplifier, because if we lock to F2, we can effectively remove all other effects from the spectrum. We use this technique to create a spectrum analyzer using our ADALM Pluto. I'll put a link of the previous videos in which I talked in detail about these techniques down below. But just another recap to see how we can actually implement this using our ADALM Pluto. Basically, ADALM Pluto gives us the exact tools to do those multiplications because at the receiver after the LNA, we have these mixers that uh, that uh, that are first of all that are quadrature mixers, meaning that if this is a sine, the other term is cosine, and then right exactly it does the same that does exactly the thing that we want it for us. It multiplies the input received signal to a sine of f and a cosine of f, and then sends it to the ADC and sends the information back to the RX buffer, where we can just apply very accurate and very powerful low pass filtering. The accuracy of this down mixing is determined by how accurate is the LO frequency of this mixer, which is set by these oscillators inside our ADALM Pluto. Another powerful thing that we have here is this LO frequency can change from 70 megahertz to 6 gigahertz, which can give us a very wide range spectrum analyzer because we can just sweep the LO frequency from 70 megahertz all the way to 6 gigahertz to look at all the spectrums. Very powerful device. Okay, so before moving on to the code and showing the demo, just want to giving a conclusion was that we have this SDR. We can use the lock-in amplifier technique to make a spectrum analyzer from it by just sweeping the frequencies, and for each RXLO frequency, mixing the received signal by that RXLO, then you sending that DC term to our RX buffer and then applying a low pass and then repeating it for all the frequencies, right? Okay, so now let's move to the code briefly, and then we'll go to the demo. Okay, just I briefly I'm going to talk about the code. I'm uploading the code to the GitHub, so you can take a look yourself. But this code, one of the things that I try to add to it uh, compared to the previous code I showed in the previous videos is I have made it more configurable, meaning that because uh, because as an spectrum analyzer, we want to have the ability to change the start or a stop frequency of the sweep or number of the sweep. I have added them into the GUI, so you can just change this number and press apply to change the uh, all important things about the spectrum, the stop, starts, steps, and also sample rate or the filter bandwidth of the filter after the down mixer. Also, one other interesting thing is because we have a low pass filter after ADC data is captured, we apply a low pass filter. I have added another variable which is basically cutoff frequency of that filter that can be changed in our GUI. The reason is that um, if you have worked with an actual spectrum analyzer device, you know that um, based on your based on the sweep range and your sweep steps, you need different resolutions for your low pass filter if you want to um, go for very high accuracies and high resolutions in your frequency axis. If you want to, for instance, capture the frequency differences within 100 kilohertz, you need to your low pass filter to cutoff frequency to at least be one decade below that resolution in frequency axis. Usually, in a spectrum analyzers, these resolutions are can be changed in the device as well as the sweep frequencies. But it definitely means that as you increase the resolution, you make the accuracy better, your sweep time is increased. Um, and as always, we have after this we set all these frequency all these configurations for our ADALM Pluto. We first connect to it. We set the sample rate, RxLO, buffer size, and also the control mode, which is the control for our variable gain amplifier. Uh, because in this spectrum analyzer, we don't want the VGA to have any effect on our captured amplitude. You just set it to manual and set it to some amplification. This can change, of course, based on the environment or the requirement you have. Then one other thing that I want to talk about is this function that is for designing the low pass filter. In the GUI, as we change the sample rate and cutoff frequency, the the FIR filter coefficients need to change, which is done in this design filter function. And basically, we just use, as I mentioned in the previous video, we just use this function to create a Kaiser. Uh, uh, Using Kaiser windowing, we generate a low pass filter. What we need to do is the cutoff frequency changes. We are also giving the width of the transition, meaning how sharp our low pass filter needs to be. I set this to 10 kilohertz. As you reduce this, definitely the order of the filter increases and more uh, computation is required. For this, I just set the width to 10 kilohertz. So first here with this function and uh, the order of the filter and beta of the filter is calculated and then an FIR low pass filter is made. Uh, then the rest are some visual plotting that you can see in the code and the sweeping of the frequency. is set as before um, in the previous videos. Also, one thing I want to show is that we are also generating some masks based on the dictionary that we defined here. As I mentioned earlier, this dictionary, I just try to make a dictionary based on the known frequencies that I expect in the environment around me. This dictionary definitely can change, and based on this dictionary, um, the new masks will be added to the plot. Okay, now that this is finalized, and now I've shown you a snippet of the code, let's go run it and see how the results look. Okay, I have started the script for some time for first sweep to be done. You can see the first sweep is in red and the new one is in blue. Uh, you can see the spectrum around the environment that I'm in this plot. I am also showing the setup as well. Basically, I have connected the ADALM Pluto to the antenna that comes with the package. This is not uh, a very good antenna. I can say it's somehow reasonable, but it's definitely not the best antenna to for this application. In fact, in another video using our frequency analyzer that we made with ADALM Pluto, I'm going to show actually um, the transfer function of the antenna and the antenna because the antenna has some null frequencies in it. But for this purpose, I just thought to go with this antenna. You can see the spectrum. The sweep starts from 100 megahertz all the way to 6 gigahertz, and the number of points for this case is 2000. And also you can see the masks that I've defined in the dictionary. You can definitely change these masks in the code based on uh, the region you are in. But some of the frequencies really are shown here. In fact, we are receiving very powerful tones at those frequencies, for instance, LTE 700 and GSM 850, uh, meaning meaning we are receiving these cell phone signals here, and also some other GSM and LTE signals here. One thing is that the area that I'm in fact, doesn't have very good cell phone reception, so uh, I don't expect these to be very powerful tones, but you can easily see uh, beside these low frequency tones that some of it might be for FM radio, we are still receiving very high tones in GSM and LTE bands in the environment. Also, you can see at 2.4 for Bluetooth and Wi-Fi, we are receiving very high tones. Uh, that in fact shape like uh, very small very narrow channels that are separated uh, very narrowly from each other, and then the Wi-Fi. Uh, I'm also going to change the sweep frequency to look at Wi-Fi 5 gig more, because I just want to show how an OFDM modulated signal looks like. As you know, Wi-Fi uh, uses OFDM to generate subcarriers that are very that are uh, close to each other. For instance, they are separated only 312.5 kilohertz from each other. I just want to show that OFDM and because we in the future videos, what we want to do is actually based on these tones, we want to go and zoom in each of these tones and see if we can uh, detect the modulations in that tones and see if we can see any other information. detect any other information. Just one more thing that I want to talk about is definitely ADALM Pluto is not the best device to be used to generate these very high uh, um, high range spectrum analyzer, because I believe some of the anomalies we see here, for instance, at this 4 gigahertz, are due to some of the effects that are inside the integrated circuit. Usually, what is done in integrated circuits that need to cover very wide range of frequencies um, is that the blocks are grouped to low frequencies, mid frequency, and high frequencies. Meaning that, for instance, we don't have an oscillator that is able to generate the entire 100 megahertz all the way to 6 gigahertz. Usually, this is done by 2 or 3 different oscillators that are switched based on the RXLO that we said. Also, we may have dividers in their way after the oscillator to generate this wide range. And one thing that happens is when we switch between the oscillators, definitely some of the properties of the new oscillator might be slightly different from the previous oscillator, adding some uh, uh, instant changes to the behavior of our ADALM Pluto. This is not only for oscillator, but also definitely VGA might be also divided into different frequency ranges. So there might be a chance that at this 4 gigahertz also VGA or LNA also are switching to adjust to a higher frequency LNA that is supposed to be used for 4 to 6 gigahertz. Okay, I don't want to make this video very long. I'm trying to divide the informations that we can gather from this spectrum analyzer into separate videos. We are going to look at different details in separate videos to not make every video very long. But just one last thing I want to show is I want to change the frequency span to just look at this range to see if I can, with some good accuracy and frequency resolution, see the OFDM modulated Wi-Fi. What I'm going to do is, let's say I change the sweeping to 5.5 gigahertz to uh, 5.6 gigahertz, and number of points 4,000. Um, and let's see if I apply that, a new sweeping will start. I'm going to let this run for some time and then come back to see if we can get any information from this. Okay, so I have zoomed in to a very small range from 5.51 to 5.53 gigahertz. I had to adjust the span a little bit to just because I wanted to show you a more dense area, like a very shorter area, and set the number of points to 2000. You can see there are very interesting things in the spectrum we are looking at, because there are several, like many tones here, but also, for instance, here you see around 5.52, there is a larger area that many of the frequencies have higher power. This happens in another channel, which is a little further from this. See, the same thing happens, and also you are see very various tones around here. So first, this is very interesting, but I just want to show you how powerful can this spectrum analyzer be, because we are seeing various effects, various tones here that definitely can help us to identify what is happening in this area. But because I don't want to make this video very long, I just want to, I won't go into the detail more, but in the future videos, we want to see what are these based. First, we need to understand how Wi-Fi works, what are the modulations that are used um, in Wi-Fi. We are going to look at different techniques, OFDM, QAM, and etc. First, we are going to learn them, go over them, try to make a transmitter and receiver from them. Then see what other things Wi-Fi has, what are the channel allocations for Wi-Fi, especially this 5 gigahertz, and what should we expect from Wi-Fi spectrum, and if this makes sense or not. Um, so yeah, this is about this video. I hope you enjoyed it. Please follow us, please subscribe, and also please go and download the code and use it. I really appreciate it if you can share this video and subscribe to channel, so to support us, so we can go uh, step by step to investigating more complicated and more sophisticated RF concepts, modulation techniques, protocols, and etc. But we need your support. Please support us, and I appreciate the help, and thank you.